Good day, Dr. Femiani and Rakesh. This is Team 5. We are presenting Project 2. So, just to give you a little background on the objectives for this project and Logica. As software engineers, it's definitely not enough to just know how to program and learn about the logic behind each programming language, but it's also very important to know what's the back end of programming languages and how they actually work. And so that was the goal for this project. Creating Logica has given us the opportunity to really explore these things. From lexical analysis, parsing techniques, creating grammar, understanding semantics, learning about intermediate code generators and virtual machines, we learned a lot about going through the different steps needed to create a programming language for this project. And each step will be explained in details in the next sections. But first we'd like to explain a little bit about Logica. So the word Logica is Latin for logic, and that is a perfect one-word descriptor about what our project is about, which is essentially a logical programming language. So Logica is a simple logical programming language that is inspired by C and Pascal. The way variables are declared in Logica is very similar to how they're declared in C, and scoping is inspired by Pascal. So the way scoping works for this language is every block, the beginning of every block starts with the keyword begin, and it ends with the keyword end. Logica is a higher level language that is easy for developers to use. When creating Logica, we tried to make it as close to human languages as possible by using keywords such as begin, then, just common English words that make it easy for the developer to understand. To download Logica, visit the Bitbucket repository link as shown here. So click on the download section of the repository, and then click on Download Repository. And then find a place to save it that you'll be able to easily find it in. I'm going to save it on the desktop. And once you download it and unzip the folder from your terminal, you need to cd to the repository folder. So right now I'm just changing the directory to the repository folder. And if you look in the repository folder, there's a script file named Logica-installer. So make sure you run this .sh file from your terminal. So now you can pretty much run Logica from anywhere, and it's installed on your machine. So then go back to your directory and find sample programs, and run any of those files using the command Logica, the name of the .lgc file, which is hello world, and then you run it. So here it gives you a confirmation saying you entered the file hello world.lgc, and it's generating the intermediate code, and it gives you the output. So when you run any .lgc file, then the intermediate code will be generated first, then it will be compiled, and the output will be shown on the screen.
Before we start explaining the functionality of the language, I would like to give a couple of notes about the project structure. First of all, this language only works on Mac. It won't work on Windows or Linux. The second thing I want to address is how the jar folder is structured. So when you first download the jar folder from our Bitbucket repository, you will find these folders shown here. The data folder, first of all, has all the sample programs that are written in Logica, and they are in the extension of .lgc. The doc folder, on the other hand, has the documentation of this project in terms of manuals, presentations, and videos. The last folder is the source folder, which has all the essential parts of the language. So it basically includes the grammar file, the main visitor class, the main class, the string template, and also the intermediate file in which the intermediate code will be stored in.
Hi, this is Subhranshu. I will be discussing 4 features of our language, which is called Logica. So let's start with variable declaration and arithmetic operations. Um, as you can see, our language starts. We need our language to have one main function. So every program in our language, we need to have a main function, and our main function start with the scope, begin and ends with end. It's very straightforward. It's human. It's quite easy to understand. And so let's start with the declaration part, variable declaration part. And as you can see, we have a integer primitive type, and and x is of type int, which holds the value 3. And let's talk about arithmetic operations. Its arithmetic operation is very straightforward here. As you can see, we are manipulating the value of x by adding 1 to it and storing back the value to x. So when we want to print the value, we just need to write colon and the value. It will print the output as 4. So it looks very straightforward. Then let's talk about if-else statement. Like any other language, any other powerful language, our language Logica also supports if-else statement, conditional statements. So let's start with the structure of if-else statement. As you can see, the if-else statement looks very easy to understand, like if, then condition, then do something else, then do something else, and end. So let's begin. We have declared a value x equal to 1, and we are comparing, and x is of integer type, and we are comparing x with 1. So x1 is not greater than 1, so it will go to the else part and it will return smaller. So this is a very straightforward example of a if-else statement in Logica. Uh, so let's talk about loops now. Um, in loops particularly, we like every other programming language like C, Java, Python, every other programming language supports loops are really good tools for repetitive work. If you don't have to repeat, you don't have to write um things more. If you don't want to write more things more than once, then you just have to repeat those with loops. So let's talk about the structure of the loop here. As you can see, the integer int um, x equal to 0. It's x is an integer type of has a value of 0, and I want to repeat this for 3 times. So the loop start with the um, repeat is a keyword, then number of times you want to repeat, then colon, then after that the body of loop starts, and it ends with an n. So inside the body we have x equal to x plus 1 and write x. So what will happen is it will increment the value of x each time it iterates over and writes the value back in the output as 0, 1, 2. So this is very straightforward and easy to understand. Let's talk about function. Function is really very important when you don't have to you some sort of functionality if you want to have in your need to have in your program, and you don't have to write code each time, and you just have to call the function and send some value, or and it will return some value back, and you just use that value in your program. So every other programming language supports function, and in our programming language we also have function. And let's talk about the structure of function. So we have declared function inside our main function, and and the user-defined function fun has a return type int, and also takes an parameter int of integer type, and it begins with begin statement, begin keyword, and ends with the end keyword. And if you want to call the function, you have to write two arrows after that, the function name, and if any parameter if the function requires. So let's talk about this example. In this example, when you want the result back as when you call fun with passing 2, it will go to the declaration part, definition part, and in here, as you can see, it will double the value as n equal to n plus n. It will return 4. After that, it will subtract 1 from it and return 3 as a result, as you are storing the back into result, and you're writing that in as output. You can see 3 will be the output. So this is why quite straightforward. And also you can see that we don't require the Logica do not need a semicolon to end the statement, which is a good thing.
Although Logica is a basic and simple programming language, it is powerful enough to support recursion. Since we have already implemented functions, function calls, and also if else, it was pretty simple and straightforward to implement recursion, because simply a recursive function is just a regular function that keeps on calling itself unless the if condition was not satisfied. So as you can see here on the slide, we have implemented the factorial using a recursive function. And in the beginning, we are declaring a function called factorial, where we are passing a variable of type integer. We're checking if n is greater than 0. If that was true, then we are calling factorial back. If you remember, this is the way we call functions in Logica. So we are calling factorial back with n minus 1, and we are multiplying the result by n. That will keep on going unless n was equal to 0. If it was equal to 0, then it will basically just return 1. At the end of the function definition, we are declaring another variable called result of type integer, where we are calling factorial with a value of 4. Then we are writing the value of result. Now I will show a demo on how to actually run this code on Logica. So in our repository, under the folder data, there are all the sample programs that we are representing here on the slide, and Factorial is one of them. It basically has the same code I just showed on the slide. So I will show now how to run this code on the terminal. So if you just type in the word Logica and pass the file name as an argument, it will run the code inside that file. It has entered the file Factorial. It's generated the intermediate code. Now it's compiling the intermediate code, and the result of factorial 4 is 24. Another cool feature about this programming language is that it has a built-in stack. So all the developer needs to do is just to declare the stack, giving it whatever name they want, push and pop values from the stack as seen here. So in this example, I'm declaring a new stack called S. I'm pushing first 2, then 3, then 4. Then I'm printing S, then I'm popping one value from S, and then I'm printing S again. Let's see a demo. Here is the same code that I was just talking about, and it's in a file called stack.lgc. Now I will run this code from the terminal. As we said, we just need to give the file name as an argument. The file name in this case is called stack. Here it has generated the intermediate code inside this file, and here is the output of the function that I just gave. So as you can see, I have printed S after I pushed 2, 3, and 4. Then I have printed back S after I popped value from S, which was 4. So here is the print value before the pop, and here is the value after the pop. Next, I will talk about how did we create this programming language. First, we went through the lexing and parsing phase, and for that we have used a tool called Antler version 4. Antler basically helps developers create their own lexer and parser by giving the grammar. So here is a sample of our grammar. It's not all of it, it's just a sample. And as you can see here, our grammar always starts with a program. So a program has to have a main function and an optional user-defined function. The main function is basically the keyword main, and then begin, and then the body. A body can be either a type of declaration, a statement, expression, a number, or stack. As you can see here, each of those pieces of the grammar will be expanded and defined further and further in the next steps. Here we are defining what a declaration can be. It can be a number declaration, car declaration, bool, or a string. And here is the definition of each type of declaration. The next step towards creating this programming language was creating a parse tree and visitor class for each parse tree. So here is a sample code that I have written using Logica, which basically declares a function called func, takes a variable y and checks if this y is equal to 2, or if it was, then it writes y is already 2, else it assigns y to 2, and then I'm calling the function and passing 2 to it. So the parse tree for this simple program code is this kind of tree. As you can see, each word or each token in the previous sample code was given an identifier. It started with a program, it had a main function, and it had another function that I called fun. And here is the parameters of the function. All of this part is the body, and here is the end statement of the function. So for each sample program we give to Logica, a parse tree similar to this one will be created. After this parse tree is created, we are creating a visitor class, which basically visits each part of our grammar and does the corresponding functionality to it. Now I will show a sample of our visitor class, which looks like this. It's called Logica main visitor.java. And as you can see here, for each piece of grammar we have, there is a visit class for that grammar. So there is a function called visit program, visit main, visit begin, visit end, and so on. And inside each visit class, we are generating the intermediate code of that part of the sample code. Then we are taking that intermediate code and running it through our VM.
Hi, I'm Akshya, and I'm going to walk through the intermediate code generation part and the VM part of our language, Logica. For the intermediate code generation, we have chosen to use the tool String Templates. String Templates is very much compatible with Antler, so we are going forward with that. In this slide, it is an example of how our high-level language print statement can be broken down into an intermediate language. In this slide, we have given a perfect example of how exactly a part of our high-level language can be converted into intermediate language. In string templates, 3 basic steps are followed to convert to the intermediate code, which is, first we create the stg file or .stg file which is a compilation of all our templates. It's a group file. And then we use the .add function to inject the attributes or create the intermediate code. And then we use the .render function to apply or render our settings. For example, in this slide we have explained of how to convert the condition part of our if-else statement into intermediate file. First, a condition statement expects three different parameters or attributes, which is going to be the left, the right, and the operand, which is defined. And then we create a stg file and then an st, which gets the instance of the const, which is nothing but the condition statement in our intermediate file. Now, when you see the second image, it explains that the condition statement expects three different parameters, which is operand, left, and the right. This is added or injected by using the st.add function and by using the .render. So our intermediate code is now generated, which expects the three parameters for every condition statement of the if-else, which is the left, right, and the operand. In this way, we can inject the attributes and create the template for all our functions or facilities we need for in our high-level languages. Now moving on to the running the intermediate code on the VM part. For our project, we are going to run the intermediate code, that is our .stg file obtained from the string templates tool on our VM, which is a modified version of the mini VM provided by Dr. Femiani. In the VM provided by Dr. Femiani, we have made a few changes because some of the functionalities which we needed for our code was not provided, and we have enhanced it according to the requirements of our project. We have included code for the while loops and also for creation of the stack, and we have also enhanced the if-else statement part of our code. Now, when the intermediate code file, that is the .stg file, is fed into our VM, our project is complete, and our Logica files can be run on the command line. The commands can be given on the terminal, and also the output is also obtained in the terminal. So this is the intermediate code generation part and the VM part of a project. Thank you.